All right, let's talk about sodium. And the point of this is that the hash algorithms like MD5 and SHA-1 are not really, and SHA-2 and all that jazz, are not perfect for cryptographic purposes. And there are newer, more uh, secure, stronger algorithms available for each of these purposes, but they're not commonly understood. And sodium just automatically moves you to the newer, more modern algorithms. So I've got it going here in my Google Cloud Service Colab. Shrink that font a little bit. All right. So I install it with pip to get the PyNaCl, which is sodium, NaCl, sodium chloride, just salt, and that's the name that's been ported to all these different languages, including Python. And now I import some functions like secret, utils, and PW hash. And to learn about secret, I can print a directory of the library, and that will show me what the names of the methods are. And you see the NACL secret library has a thing called secret box. And if I look at what's in NACL secret box, it has parameters in here, and one of the parameters is key size. And if I print key size, it's 32. So 32 bytes, which is 256 bits. So you didn't have to tell it how long a key you wanted to use like you would with AES. It just chooses the recommended length, which is 256 bits. And you can also do help to get a help message explaining how this thing works. And the thing that's interesting to us is how the secret box class works. So that's down here. Here it is, class secret box. And that'll tell you how it works. It encrypts and decrypts messages using the given secret key, which is all we care about. All right. So let's see how I can get to the bottom of this thing. All right. And there, make another. All right. So now we're going to do key derivation. And there's a thing called Argon2, which is a more modern key derivation function than the PBKDF2. It was the winner of the password hashing competition, which was extremely interesting. And by the way, if you go to Vegas for DEF CON, if you go to B-Sides Las Vegas, they have included PasswordsCon as part of it for the last several years. And PasswordsCon is very interesting. I thought, how interesting could passwords be? But they brought all these European cryptographers with better ways of making password hashes, and it was very interesting. I often hang out at PasswordsCon when I go to some hacker summer camp. So anyway, here's the hashing algorithm. You can do the same thing, and the help function will tell you how the key derivation function works. I do need to have this part done. The rest I don't really have. The rest is just informational. There. This will define KDF to be, there. Salt, password hash, argon2i, the key derivation function. And down here, it'll tell you how it works. You have the size, password, salt, and some other parameters. And there's a general rule of the salt library that there might be parameters, but they're mostly optional. And the default is the recommended value. So you don't have to worry about things so much. So all I really have to do, I'm going to generate a random salt here. I define this thing to be random of salt size. And I set salt size to be whatever size the salt library recommends for this. So that should do it. All right, there's a random salt, which of course different than what I have here. It's just, I think 16 random bytes. Now I'm going to use key derivation to derive a key from the password top secret, which is of course not very secure, but it's going to encode it in Unicode, and then it's going to use that password and that salt to make a key. Notice I didn't tell it what hash algorithm to use, and I didn't tell it how many cycles to do, but it was enough that it took a while. It takes 10 to 20 seconds to calculate, which is the point. You want to choose a hashing algorithm that does like 10,000 cycles of hashing or something, so that it takes a long time to calculate one hash, because then if someone's trying to crack your hash, they take a dictionary of like 1,000,000 hashes and they calculate all these 1,000,000 passwords and they hash them all. And if you make it so it takes a long time to calculate each hash, then it's very difficult for them to have a large dictionary. So that's the idea. That's for security. All right. And so now I have a key. generated from the password, and this is the key. It's this long 256-bit random quantity. Now I can encrypt a message. So I can take a message of hello, not text, but code. All right. And I can just encrypt it and print out the ciphertext. And there's the ciphertext, just long random code. Notice it didn't matter that I only have a 5-letter message. I don't have to make it 16 characters long to fit in a block or anything. It just takes care of all that. It pads it with something as needed, and I don't have to worry about it. And now I can decrypt it with just box decrypt. And it comes out as hello. So that's now the only part of this that's annoying is it's hard to manipulate a hexadecimal blob like this, especially since some of the characters are printable. So the T and 4 were printable characters, and then the rest of the bytes are \X F7, and then this character was printable. So this format is really miserable to communicate data. Well, that's why you use base 64. So if we do this, that's why base 64 exists. It originally existed to email images, and now you use it anytime you need to translate binary data into something you can print and understand. So I take the decode and turn it into base 64 text. And then I think I'm going to have a print here. Yep, I didn't print it, because in this Python environment, I have to explicitly have some of the prints put in, as opposed to a normal interactive Python environment there. So now that's the ciphertext, and that's a much friendlier way to move it around. Now you can put in a string and print it out and all that jazz. All right, so that's private key encryption with Sodium. And there's an analogous public key encryption algorithm available with Sodium. And again, you install Python, or you install a Pinacle, and now you have public. You can fork private key in box. So you generate some keys, and off it goes, creating a generated key here, which is just a long thing. And then you generate keys at the other end. Just like any public and private key system, each person has to generate their own private keys and then make their public keys available. And now I take Alice's public key. Bob is going to send a message, hello from Bob to Alice. So he needs to get Alice's public key. And that's going to be PK Alice here. We defined it up here, PK Alice. So you have to have her public key, and then you encode it, and it's just pretty easy to read, nothing baffling, and that will create the ciphertext, which is here in hexadecimal, and that text can only be read by Alice, nobody else, because she holds the private key. So she can decrypt it, and that depends on her possession of the private key, and get it. So that's all. Just wanted to show you that. This is the recommended library, although, of course, Sodium was written before we started worrying about post-quantum algorithms. So this public key algorithm is probably going to have to change. I imagine it's using elliptic curve cryptography, which is considered the most advanced and efficient algorithm of the current public key systems, but it really should be upgraded to Kyber or something pretty soon. And even when it is, I imagine it will conceal all those crazy matrices and polynomials and just make it easier for you to use by abstracting away that stuff, which is baffling. But that had not happened as of the time I wrote this project, which is about 4 years ago now. So I should take a look. Sodium may have a post-quantum option by now. Anyway, that's all I wanted to show you about Sodium.